This video is part 1 of a review of Unit 4 of AP Calculus. In this video, we will talk about L'Hopital's rule, inverse trig function derivatives, and related rates. For problem number 1, we need to find the limit of this expression. Let's do direct substitution and see what happens. We get this. Sine of 0 is 0, so that means that the numerator is approaching 0. And e to the 0 power is 1. 1 minus 1 again is 0. Because the numerator and the denominator are both approaching 0, we can use L'Hopital's rule, which says that we can take the derivative of the numerator and the derivative of the denominator without changing the value of the limit. This would also work if the numerator and denominator were both approaching infinity. By the way, this step right here is mandatory. You must show that the numerator and denominator are both approaching 0 by writing a separate arrow for the numerator and the denominator. Anyway, let's take the derivative of the numerator. The derivative of x is 1, and the derivative of sine is cosine. How about the denominator? The derivative of 1 is 0, and then I have negative. The derivative of e to the x is still e to the x. Let's see what happens if we do direct substitution now. So we have 1 plus cosine 0 over negative e to the 0 power. Cosine of 0 is 1, so this is 1 plus 1. E to the 0 power is 1, so over negative 1. So this is 2 over negative 1, which equals negative 2. So that's the answer to number 1. Number 2, let's take the limit as x approaches 0 of this expression. Let's start with direct substitution and see what happens. The numerator is 0. The denominator will be arc sine, well, 3 times 0 is just 0. When you evaluate arc sine, you're thinking to yourself the sine of what angle is equal to 0. And we know that the sine of 0 is 0. So that is the value of arc sine 0. In other words, the numerator and denominator are both approaching 0. Because the numerator and denominator are both approaching 0, we can use L'Hopital's rule, which says we can take the derivative of the numerator and the denominator without changing the value of the limit. You have to show this little step with the 2 arrows separately. We have memorized that the derivative of arc sine x is 1 over the square root of 1 minus x squared. So keep that in mind. The derivative of x is 1, and the derivative of arc sine, as I just mentioned, is 1 over the square root of 1 minus x squared. However, because this is not just an x in here, it is a 3x, then we have to do the chain rule and multiply by the derivative of this inner function. And the derivative of 3x is 3, which I will put in the numerator. So we have this. When you divide by a fraction, you multiply by the reciprocal. So I'm going to flip this upside down. So now we have this. Let's go ahead and try direct substitution. So we get the square root of 1 minus 3 times 0 squared over 3. 3 times 0 is 0. Square that, it's still 0. So we really just have the square root of 1, which is 1. So the limit is 1/3. For number 3, as always, let's try direct substitution first and see what happens. So we will have 1 squared minus natural log 1 over 4 times 1 minus 4. But 1 squared is 1. Natural log of 1 is 0. In the denominator, I just have 4 minus 4, which is 0. So I'm ending up with 1 over 0. So the limit simply does not exist. All right? When direct substitution gives you a constant over 0, that means that the limit does not exist. So we don't need to do L'Hopital's rule or anything like that. Number 4, consider the function f of x equals arcsine radical x over 2 on the closed interval from 0 to 4. Let's find the derivative of f of x. We know that the derivative of arcsine is going to be 1 over the square root of 1 minus x squared. But because we don't have a simple x in here, instead we have radical x over 2. We need to then multiply by the derivative of this inner function. So consider this. Radical x over 2 is the same thing as 1/2 times x to the 1/2 power. Right? Because we're dividing by 2, so that's where the 1/2 is coming from. And square root is the same thing as the 1/2 power. So when I take the derivative of this inner function, I'm doing the power rule, and I'm multiplying 1/2 times 1/2. So that's going to give me 1/4. Then I subtract 1 from the exponent. So that will give me the negative 1/2 power. So this is what I'm really multiplying by. Maybe I'll keep going for a second. So because this is the negative 1/2 power, I'm going to drop this down to the denominator. So see the 1/4? In the denominator, I will have the square root of x. So this is the derivative of the inner function. So I need to multiply by this. Inside this radical, if I square the numerator and denominator, squaring the radical x is just x. If I square the 2, I get a 4. So now I have this. I'm looking at the answers, and I see that none of the answers have a fraction under that radical. So somehow I need to multiply by something that's going to cancel out this 4. What am I going to multiply by? Well, I'm already set to multiply by 4 radical x. So maybe I can use that to my advantage somehow. However, I don't want to just put 4 radical x here, because you cannot multiply a regular number times a radical. If I tried to, the 4 would just sit out in the front and it wouldn't cancel out anything. So if I want to be able to get this 4 inside the radical, I need to put it under a radical. Obviously, I can't just stick a radical on the 4 because that would change the value. But what I can do is I can write the square root of 16. Think about it. The square root of 16 is 4, so these are the same. Now that we have a radical, I can actually multiply through and do the distributive property with the 16. In fact, since we have radical 16 and radical x, I can just write this as radical 16x. So in a minute, when I do the distributive property, I'm going to end up multiplying 16x times each term. 16x times 1 is 16x minus 4 goes into 16 4 times, and then x times x is x squared. We have a common factor of 4, actually 4x, but focus on the fact that both of these are divisible by 4. So here I have factored out that common factor of 4 outside of the parentheses. In this form, it's easy to see that I can go ahead and take the square root of 4 right now and then put that result outside of the radical. So I end up with this expression. Let's take a look and see what we see. So I have 2 times radical 4x minus x squared. 2 times radical 4x minus x squared. The answer is D. For number 5, we need to find the absolute maximum of f of x on the closed interval from 0 to 4. To find the absolute maximum, we need to do a candidates test. So we need to develop a list of the possible locations of the absolute maximum. We already have 2 candidates right away because the beginning and the end of the closed interval are possible candidates. The only other possible locations of the maximum value will occur when f of x, when f prime is either equal to 0 or when f prime is undefined. So let's consider each of these. Where is f prime equal to 0? So here's f prime. A fraction will only equal 0 when the numerator is equal to 0. But we just have a constant in the numerator. So f prime can never equal 0. So we can forget about that option. So the only other candidates will occur when when f prime is undefined. And this fraction will be undefined when the denominator is equal to 0. So we need to solve this equation. When you think about it, this expression will only equal 0 if the stuff inside the radical is equal to 0. That's the only way. So we can really just skip straight to this. 4x minus x squared is equal to 0. If it makes you feel better, if you don't like that logical leap that I just made, you could divide both sides by 2. That'll get rid of the 2. And then square both sides. That'll make the radical go away. And then you'll end up here. Anyway, let's solve this by factoring. I see that we have a common factor of x. So if I take that out, then that leaves me with 4 minus x. So setting each of these equal to 0, I get x equals 0 from the first factor. And I have x equals 4 from the second factor. So we have, well, I started to say we have 2 additional candidates, but take a look, x equals 0 and x equals 4. These are the candidates we already had from the ends of the interval. So I guess 0 and 4 are the only candidates. Label your table as a candidates test. And we're just really making a T-chart, old school. In the first column, we're going to put x, and in the other column, we will have f of x. And here are the candidates, 0 and 4. Remember that f of x is arcsine radical x over 2. So f at 0 will be arcsine radical 0 over 2, which is really just arcsine 0. Again, when you evaluate arcsine, you ask yourself the question, the sine of what angle equals 0? And we know that the sine of 0 is equal to 0. So arcsine 0 is 0. Now let's evaluate f at 4. So we have arcsine radical 4 over 2, but that's just arcsine. Well, square root of 4 is 2, so this is 2 over 2, which is 1. And when you ask yourself, sine of what angle is equal to 1? The answer is pi over 2. The sine of pi over 2 is 1. Between these two, pi over 2 is the greatest. So f of x has a maximum value of pi over 2 at x equals 4. Just for fun, here's what that looks like on Desmos. Notice that the maximum value occurs at x equals 4, and the maximum value is pi over 2. For number 6, we need to find the derivative of f of x equals arcsecant x squared minus 1. We have memorized the fact that the derivative of arcsecant x is 1 over the absolute value of x times the square root of x squared minus 1. Let's go ahead and find f prime. Obviously, we have to use the chain rule because we have a function inside of a function. But let's start out with the model that I just reminded you of. So we have this absolute value in the front, and we have the square root, and we have x squared minus 1. I'm leaving all this empty space because we don't just have x, we have x squared minus 1. So that has to go on the inside. So we have x squared minus 1 here, and we have x squared minus 1 here. Because we have this function inside of a function, the chain rule says we have to multiply by the derivative of the inner function. The derivative of this purple stuff is 2x, which we will put in the numerator. Now they told us not to simplify, so this is the answer. Number 7. Point A moves downward at a rate of 2 feet per second. Point B moves to the right at a rate of 3 feet per second. At a particular moment, we are given the following. Blam, blam, blam. At this moment, at what rate is the hypotenuse h changing in feet per second? Clearly, this is a related rates problem. I like to write down any rates or other facts that we are given to begin with. So point A is moving downward at a rate of 2 feet per second. So we can say that dy dt equals negative 2 feet per second. Negative because it is moving downward. And then point B is moving to the right at a rate of 3 feet per second. So now we are talking about the change in x. So we know that dx dt is equal to positive 3 feet per second. And we know it is positive because it is moving to the right. And we have these facts right here, which I will just highlight instead of recopying. So what are we trying to find? What is the rate? At what rate is the hypotenuse changing? So we need to find dh dt. We need a relationship between x, y, and h. The obvious relationship is the Pythagorean Theorem. X squared plus y squared is equal to h squared. We need to make dy dt, dx dt, and dh dt appear. So of course we are going to take the derivative of both sides with respect to t. So we're going to do d dt on both sides of the equation. So let's go term by term. Be careful to use the chain rule because these letters don't match. The variables don't match. So the derivative of the outer function is 2x, but then we have to multiply by the derivative of the inner function, which is dx dt. And then same thing for the y. The outer function, the derivative is 2y, but then we multiply by the derivative of the inner function, dy dt. And one more time, the derivative of the outer function is 2h, and the derivative of the inner function is dh dt. Now it is time to make some substitutions. We know that x is 12 at the moment in question. Dx dt is 3. Y is 5. Dy dt is negative 2. And h is 13. So let's make all of those substitutions. So far we have this. Remember, we are trying to find dH dt, which is the only unknown in this equation. So if I want to get dH dt by itself, I can simply divide both sides of the equation by 2 times 13. So if I didn't feel like working all this out, I could just put the 2 times 13 right here, and there it is. I have dH dt by itself. So this would be an acceptable answer. All right, just for fun, I will go ahead and work it out, but you are allowed to leave your answers like this. Well, not exactly. I should go ahead and put the units in. So we're talking about the change in h with respect to time. So this should be feet per second. All right, now it's an acceptable answer. All of this simplifies down to 2 feet per second. So this is the final answer.